Welcome back to Sleepy Science Facts, where curiosity unwinds and science drifts softly into your evening. Tonight, we're floating gently above our home planet, Earth, a world filled with quiet wonders you may have never noticed. In this calming journey, you'll learn how Earth formed, why it's so uniquely balanced for life, and a few soothing facts about the forces that keep our world steady beneath our feet. So settle in, let your breathing slow, and let the planet's story guide your mind into relaxation. Make sure to like, subscribe, and hit the bell for more sleepy science facts. And remember, read the first command for support. The story of Earth begins not with Earth itself, but with the death of another star. More than 4.6 billion years ago, in a remote corner of the Milky Way, a massive star reached the end of its life. It exploded in a violent supernova, scattering its enriched elements, iron, carbon, silicon, oxygen, into a cold cloud of gas and dust. This cloud, known as the solar nebula, drifted silently for millions of years, a glittering smear of cosmic debris waiting for something to ignite its destiny. Then, gravity began its ancient work. The nebula started to collapse, spinning faster and flattening into a disk. At its center, matter compressed into a sphere of unimaginable heat and pressure, the young sun. Around it, fragments of rock and ice collided and merged, forming the seeds of future planets. And somewhere within that swirling chaos, amid collisions so violent they melted mountains and vaporized oceans that had not yet formed, the early Earth began to take shape. This young Earth was nothing like the world we know today. It was a molten, glowing sphere, a miniature star of liquid rock. Volcanoes erupted endlessly across its blazing surface. Asteroids the size of continents slammed into it, each impact reshaping the planet, mixing its elements, deepening its gravity. The early atmosphere was a toxic haze of carbon dioxide, nitrogen, methane, and sulfur. The skies were red and orange, heavy with ash. Lightning storms raged over oceans of lava. The entire surface shimmered with heat, so intense that even the hardest minerals melted like wax under a candle. Yet amid this inferno was the raw material for everything that would come afterward. Then came the collision that changed the world forever. A Mars-sized protoplanet, what scientists now call Theia, struck Earth at an angle. The impact released more energy than any volcanic eruption or asteroid strike in Earth's history. The entire surface liquefied again. Much of Earth's mantle was blasted into space, forming a glowing ring of molten debris that circled the planet like a fiery halo. Over millions of years, this debris cooled, clumped together, and formed the moon. The newborn moon was far closer than it is today, so close that it appeared enormous in the sky, filling entire horizons. Its gravitational pull slowed Earth's violent spin and stabilized its tilt, creating tides and laying the groundwork for stable seasons. Without the moon, life as we know it might never have emerged. Slowly, over tens of millions of years, Earth cooled. A crust formed, cracking and shifting like the skin of a drying fruit. Steam from the planet's interior rose into the sky, condensed, and fell as rain. It rained for thousands of years. It rained until the world began to drown. The basins of the young Earth filled with water, water delivered by ancient ice-rich asteroids, water released from minerals deep in the mantle, water that would become the oceans we know today. And in those oceans, a quiet miracle was brewing. The newborn oceans of Earth were not calm, peaceful, or serene. They were stormy, acidic, enriched with minerals and chemicals released from volcanic vents. The water boiled near coastlines, while in deeper regions the pressure was enough to crush metal. And yet, within this turbulent cauldron, something extraordinary was taking shape. Molecules drifted, collided, broke apart, and recombined. Lightning flashed above the waves, delivering bursts of energy. Hydrothermal vents spewed hot, mineral-rich fluids into the cold, dark sea. All the ingredients for life — carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus — mixed in an endless dance. Somewhere in these dark waters, a molecule formed that had the remarkable ability to copy itself. It was fragile, imperfect, but it could replicate. And from this simple act of copying, the first spark of life emerged. Life's earliest forms were microscopic, single-celled organisms smaller than a speck of dust. They floated in the oceans like tiny explorers, drifting wherever currents carried them. They had no eyes, no complex structures, no nervous systems. Yet they possessed the greatest ability in the universe, the ability to change. These early organisms lived through chemistry. Some absorbed energy from minerals. Others captured sunlight using primitive forms of photosynthesis. Slowly, they spread across the oceans, thriving in environments that would be lethal to anything alive today. The atmosphere remained toxic. The land was barren. The sky was tinted orange. But the seas, those dark, mysterious seas, were alive, and with life came transformation. Over millions of years, certain microbes evolved an extraordinary ability. They learned to perform oxygenic photosynthesis, splitting water molecules and releasing oxygen as a byproduct. At first, this oxygen had little effect on the world. It bonded with iron dissolved in the oceans, sinking to the seafloor as rust. But as life continued to produce more and more oxygen, the oceans could no longer contain it. Oxygen began to escape into the atmosphere. Slowly, silently, the air itself was changing. This invisible shift would become one of the most important events in Earth's history. It would reshape climate, chemistry, geology, and every future life form. But with great change comes great disruption, and Earth was preparing for one of the most catastrophic transformations the planet would ever endure. As oxygen slowly seeped into the atmosphere, the world above the oceans began to transform in ways the early microbes could not comprehend. To them, oxygen was not a gift. It was poison, a threat, a molecule so reactive that it damaged their fragile structures. For countless generations, they had lived in a world without breathable air, a world shaped by methane, hydrogen sulfide, and carbon dioxide. Oxygen was toxic to their existence. And yet, the organisms producing this strange new gas, ancient cyanobacteria, continued to spread, covering shallow seas like vast green carpets, releasing oxygen with every breathless movement. The atmosphere thickened with this new element, and the ocean's chemistry began to shift. The iron dissolved in seawater reacted, forming rust that sank to the ocean floor in immense layers, creating the banded iron formations humans would one day mine for steel. It was a geological heartbeat written in stone, a testament to the invisible revolution unfolding beneath ancient waves. Over millions of years, oxygen accumulated until it crossed a threshold, a point where the world could no longer remain the same. Climate systems shifted. Atmospheric methane, once abundant, reacted with oxygen and disappeared. And methane was one of the strongest greenhouse gases Earth had. Without it, the planet began to cool. Storms raged as temperature fell. Ice began to creep from the poles toward the equator. The oceans, once warm cradles of early life, grew colder. Entire microbial ecosystems collapsed. Oxygen, ironically the foundation for future life, triggered one of the greatest mass extinctions the world had ever seen. Yet from this chemical catastrophe, the stage was being set for something extraordinary. Evolution thrives under pressure, and even in the face of extinction, life found a way to adapt. New organisms capable of surviving and eventually thriving in the presence of oxygen emerged. The world was entering a new era, shaped by the delicate balance between destruction and creation. To truly understand Earth's deep history, one must embrace a profound paradox. The greatest leaps in evolution often come from catastrophe. And the Great Oxygenation Event, occurring about 2.4 billion years ago, was one of the most dramatic catastrophes ever recorded. Before it, the atmosphere was stable, predictable, dominated by gases that favored simple life. After oxygen began flooding the skies, nothing remained the same. The Earth's temperature plummeted. Ice sheets advanced toward the tropics. Entire ecosystems vanished. It was an extinction so slow and so total that it reshaped the chemical and physical nature of the planet. Yet within this environmental chaos, life was quietly rewriting the rules of existence. Oxygen, once a deadly toxin, became the fuel for a new type of metabolism. Instead of relying on inefficient chemical pathways, certain organisms evolved to harness the immense power of oxygen-based respiration. This innovation produced far more energy than any method used before. It allowed cells to grow larger, more complex, more organized. It enabled them to cluster into communities, then colonies, and eventually into structures that would become the first eukaryotic cells. The ancestors of every plant, every animal, every fungus, every complex organism to ever walk, swim, or fly on Earth. The Great Oxygenation Event was not merely a climate shift. It was a turning point in the history of life. The atmosphere, once orange and hazy, slowly turned blue. The sky cleared as oxygen reacted with carbon dioxide and methane. Sunlight penetrated the air differently, changing weather patterns. Lightning storms diminished. UV radiation still bathed the surface, but in time, oxygen formed the protective ozone layer, shielding life from the sun's harshest rays. For the first time, the planet had an atmospheric shield, one that would make land eventually habitable. The stage was being set for a world beyond the oceans, though it would take hundreds of millions of years for life to venture out of water. Meanwhile, deep in the oceans, early eukaryotes experimented with new strategies of survival. Some consumed other cells. Some formed symbiotic partnerships, merging into new hybrid organisms. Through these unions, mitochondria, the tiny powerhouses that fuel complex life, were born. It was one of evolution's most astonishing innovations, a merging of ancient bacteria into the architecture of more advanced life. This partnership was so successful that every complex cell on Earth today still carries these once independent organisms inside them. It is a reminder that even the greatest transformations in nature often come not from competition, but from cooperation. But Earth was not finished changing. In fact, the planet was preparing to descend into one of the most extreme climates it would ever experience. The balance between sunlight, atmospheric gases, and planetary temperature tilted once more, and the transformation that followed would push Earth to its very limits. Imagine a world where the oceans freeze from pole to equator, where glaciers thousands of meters thick bury almost every continent, where global temperatures plunge to levels unimaginable in the modern age. This was Snowball Earth, one of the most dramatic climatic states ever recorded. It occurred not once, but multiple times, between 720 and 635 million years ago. And during these frozen eras, Earth was nearly unrecognizable. The cooling likely began with a subtle shift, perhaps a drop in volcanic activity, a drawdown of atmospheric carbon dioxide by newly emerging rocks, or a change in ocean circulation. But once the cooling began, it accelerated with devastating speed. Ice reflects sunlight, and as the ice sheets spread, they reflected more and more of the sun's warmth back into space. It was a runaway feedback loop. Ice advanced across continents. Oceans froze at the surface. Waves ceased. Winds weakened. The once blue planet turned white, but beneath the ice, life continued, small, fragile, but persistent. In the dark oceans, hydrothermal vents provided heat and nutrients. Chemical-rich waters allowed microbial communities to survive even when the surface world was locked in a deep freeze. Life had endured asteroid impacts, chemical catastrophes, and the rise of oxygen. Now it would endure global glaciation. And remarkably, life found ways not just to survive, but to innovate. Even in the cold isolation of Snowball Earth, evolution continued its slow, relentless march. Meanwhile, volcanic activity never ceased. Deep beneath the ice, volcanoes continued releasing carbon dioxide into the atmosphere. Over millions of years, CO2 accumulated because there were no liquid oceans to absorb it. The greenhouse effect intensified. Temperatures slowly rose. And eventually, the planet reached a tipping point. The ice began to melt. Runoff from retreating glaciers poured into the oceans, carrying minerals that sparked vast blooms of life. The world awoke from its frozen slumber, entering one of the most biologically explosive periods in Earth's history. The end of Snowball Earth marked not just the return of warmth, but the beginning of a profound evolutionary leap. The rise of complex multicellular life in shapes and forms the world had never seen before. As the ice retreated and the world thawed, Earth transformed once again into a watery, shimmering sphere brimming with possibility. Sunlight returned to the oceans in full force, igniting photosynthesis in microbial communities that had survived the long frozen night. The oceans, once dark and suffocated beneath kilometers of ice, became enormous canvases for biological rebirth. Nutrients released from melting glaciers washed into the sea, triggering blooms of microscopic life, so vast they might have tinted entire oceans green. The thawing world was turbulent, chaotic, and bursting with chemical energy, conditions that favored evolutionary leaps. For millions of years, life had been constrained by the bitter cold. Now, the sudden warmth created an evolutionary arms race. Organisms that could adapt quickly flourished. Those that lagged were left behind. And in this accelerated environment, evolution began experimenting in dramatic new ways. Cells that had once survived alone now joined together in larger, more coordinated bodies. They began to cooperate, to specialize, to communicate chemically. Primitive multicellular forms, simple yet revolutionary, appeared. Some were soft, jelly-like structures living on the seafloor. Others floated freely, their bodies shaped by currents and sunlight. For the first time in Earth's history, bodies were becoming more than single cells stitched together. They were building complexity. They were diversifying. They were becoming organisms capable of movement, perception, coordination, and even primitive forms of predation. This emergence of complexity set the stage for one of the most dramatic turning points in the history of life on Earth. The end of Snowball Earth was more than a climatic shift. It was a reset button. A new era had begun, one defined by innovation, by experimentation, by mistakes and miracles etched into the fossil record. The oceans, enriched and energized, became evolutionary laboratories. And soon, in a span of time that was geologically brief but biologically explosive, life would burst into unimaginable diversity. This was the dawn of the Cambrian period, the moment when Earth transitioned from a planet of simple organisms into a world teeming with complex, dynamic, interconnected life. About 541 million years ago, the oceans of Earth changed forever. In what seemed like an instant in geological time, life exploded into complexity. Creatures with hard shells, segmented limbs, glowing eyes, and powerful jaws emerged seemingly out of nowhere. Before the Cambrian, life had been simple, soft-bodied, slow-changing, limited in structure and diversity. But during the Cambrian explosion, evolution stepped on the accelerator, generating new forms at a rate never before seen. The reasons for this dramatic leap remain a mystery, a scientific puzzle still debated today. Some theories suggest that oxygen levels rose just enough to allow more energetic metabolisms. Others argue that genetic breakthroughs, such as the evolution of the Hox gene system, unlocked the blueprints needed to build complex bodies. Still others believe that ecological pressures, such as predation, triggered an evolutionary arms race. Whatever the cause, the effect was unmistakable: the birth of a modern biosphere. Imagine diving into a Cambrian sea. The waters shimmer with unfamiliar life, alien yet oddly familiar. Strange creatures crawl across the ocean floor, while others dart through mid-water like flashes of living light. Trilobites, one of the most iconic creatures of the era, scuttle across sediments in enormous numbers, their segmented bodies covered in hard armor, their compound eyes glittering with thousands of tiny lenses. Anomalocaris, one of the earliest apex predators, glides through the water with undulating flaps, its grasping appendages reaching for prey. Apobinia, with its 5 eyes and flexible trunk like proboscis, creeps across the seabed like a living relic from an artist's dream. Hallucigenia, long and spiny, moves with unsettling motions, as though reality itself struggles to contain its shape. These creatures were not mere evolutionary experiments, they were pioneers. They introduced the first complex ecosystems with hunters, prey, scavengers, filter feeders, and burrowers. The ocean floor became a battlefield, a marketplace, a city of life. Burrowing animals began to churn sediments, reshaping the chemistry of the seafloor and altering nutrient cycles. Predators refined their techniques. Defenses evolved in response. For every adaptation, counter-adaptations appeared. The world had entered a dynamic equilibrium in which life no longer drifted passively. It competed, strategized, and adapted with purpose. The Cambrian explosion also established body plans that would define nearly all future animal life. The ancestors of modern arthropods, mollusks, chordates, and countless others emerged during this time. Humans, in a profound sense, can trace their biological lineage back to the innovations that arose in this ancient sea. It was here that the blueprint for the vertebrate body first appeared, simple, primitive, but unmistakable. From those early chordates came the long chain of evolution that would eventually lead to fish, amphibians, reptiles, mammals, and ultimately human beings standing on two legs, gazing back into the ancient ocean that once cradled their distant ancestors. But evolution never rests. Even the explosion of Cambrian life was only the beginning. The world above the water remained barren, untouched, silent. The continents were sterile wastelands of rock and wind. Yet life was already preparing to take its most daring leap, a leap from the safety of the ocean into the harsh, unforgiving world of land. For billions of years, the land had been silent. It had known no forests, no animals, no chirping insects or fluttering wings. Only wind shaped its rocks. Only rain carved its valleys. But around 480 million years ago, everything began to change. The first living pioneers crept out of the oceans and into a world so hostile it might as well have been another planet. The transition was monumental. Water was a cradle, a protector. In the ocean, organisms were supported by buoyancy, shielded from radiation, surrounded by nutrients, and kept moist at all times. Land offered none of these comforts. Gravity pulled down with relentless force. Sunlight scorched and dried unprotected cells. The air was thin and unfiltered, filled with UV radiation. To survive on land required evolutionary innovations so profound they would reshape life forever. And the first to attempt this perilous journey were not animals, but plants. Tiny algae-like organisms colonized moist shorelines, clinging to rocks and sediments. They adapted slowly, developing structures that prevented water loss. They formed simple stems, simple anchoring structures, and eventually a waxy coating that allowed them to endure periods of dryness. These early pioneers didn't look like the trees or flowers we know today. They were low, green mats that hugged the ground like primitive carpets. But their presence changed everything. They began releasing oxygen directly onto land surfaces. They stabilized soils. They created miniature ecosystems that retained moisture long enough for other organisms to follow. Soon, fungi arrived, silent, patient recyclers that partnered with plants to extract nutrients from rock. This ancient alliance, known today as mycorrhiza, is so successful that it still supports nearly all plant life on Earth. With plants came new possibilities, taller structures, stronger tissues, the development of vascular systems capable of transporting water upward against gravity. Forests were still far away, but the foundation had been laid. And yet, even as plants conquered the land, the animal world was beginning its own daring ascent. The young Earth turns slowly in the dim glow of a newborn sun, its molten surface hardening like the cooling crust of an ancient wound. The world trembles with every heartbeat of the planet, each quake, each volcanic sigh, each spurt of molten rock forming new land where there was none before. In these primeval centuries, Earth is not yet a home. It is a battlefield of fire and stone, hammered endlessly by meteorites left over from the violent sculpting of the solar system. Yet hidden within the chaos is a quiet promise, a promise that one day, something extraordinary will awaken here. The atmosphere of this early Earth is unbearably toxic, a suffocating veil of carbon dioxide, nitrogen, methane, and ammonia swirling above seas of magma that glow like red-hot wounds under a dim sky. Lightning storms crackle endlessly, their white-blue veins carving through the thick haze, illuminating the planet with the ferocity of a world trying to understand its own existence. Volcanoes erupt in a global chorus, releasing oceans of steam that rise and condense, fall and rise again, a cycle that will, over millions of years, give birth to the first true oceans. And then, slowly, the surface begins to cool. The molten fields harden into black plains of basalt. The vapors condense more steadily. And for the first time in the history of this young world, rain begins to fall not for minutes or hours, but for thousands upon thousands of consecutive years. Endless, torrential rain, falling with the force of a planet exhaling deeply after ages of suffocating heat. These rains fill the lowest basins, forming oceans that stretch wider and deeper with each passing millennium. Steam rises in colossal pillars that wrap the planet in dense clouds, but through every downpour, Earth is steadily transforming. Slowly, the planet is giving itself the gift of water, the substance that will eventually shape every continent, sculpt every valley, cradle every creature yet to live. Standing at the shorelines of these first oceans, had anyone been there to observe, would feel like standing before the most alien landscape imaginable. The water is not the clear blue we know today. Instead, it is dark, murky, rich with dissolved minerals and chemicals carried by relentless volcanic rains. The ocean floors are lined with hydrothermal vents belching scorching water and minerals into the sea, creating chemical gradients that, in the far future, will become the stage for one of the greatest miracles in the universe. But at this moment, the Earth is still alone, still silent, still waiting. Far above, the sun glows faintly, dimmer than the star we know today, yet wild, unpredictable, and volatile. Great streams of solar wind lash out into space, but Earth's magnetic field, newly formed, strong, and fiercely protective, shields the young world like a guardian, preventing its atmosphere from being stripped away. Without this magnetic shield, Earth would have become barren like Mars, lifeless like Mercury, or scorched like Venus. But Earth is different. Earth has a defense. Earth has stability. And stability in the cosmic dance of life is everything. As millions of years unravel, the continents begin to stir. The Earth's crust, cracked and fragmented like the eggshell of a cosmic birth, begins to drift. Enormous slabs of land rub against each other, collide, pull apart, and reshape the surface again and again. Mountains rise only to crumble. Volcanoes tear apart the land only to rebuild it in new forms. Landscapes shift in an eternal dance, a slow geological heartbeat that never stops, even today. The oceans deepen. The atmosphere thickens. The planet continues to breathe, rumble, and transform. Yet something vital is still missing, something invisible, delicate, but utterly essential to everything Earth will one day become. The spark, the first whisper of life. Scientists today debate where this spark first ignited. Was it in the deep, warm pools of the newly formed oceans, enriched with chemicals and struck by lightning again and again? Or did it emerge near the hydrothermal vents at the ocean floor, where minerals and heat created the perfect crucible of chemical reactions? Or perhaps life arrived from elsewhere, carried by comets or meteorites, hitching a ride across the cosmos in frozen fragments of organic material. The truth remains hidden in the folds of deep time, but one thing is certain. At some improbable moment, from some improbable combination of elements, Earth awakens. The first molecules capable of self-replication form, clinging to rocks, drifting in water, or thriving in mineral-rich vents. They are microscopic, nothing more than simple, fragile chemical chains. But they possess something Earth has never seen before: the ability to copy themselves. And with that first copy, that first error, that first mutation, the history of life begins. It is a slow, almost humble beginning: no grand creatures, no movement, no intelligence. Just tiny, primitive cells floating in the ancient oceans, surviving one moment at a time. But even in their simplicity, they represent a cosmic triumph. For the first time in 4.5 billion years, Earth is no longer silent. It hosts something that grows, changes, adapts, and endures. Life. Against all odds, life has taken root. And though it will take billions of years for this microscopic beginning to evolve into forests, animals, civilizations, and human beings, everything traces back to this moment, the moment Earth ceased to be just a planet and became a cradle of potential, a world capable of wonder, a world capable of transformation, a world capable of becoming home. The oceans ripple under the young sun, and with each passing millennium, the blueprint of life grows richer, more complex, more daring. The crust shifts. The continents form new shapes. The atmosphere begins to change as ancient bacteria exhale oxygen for the first time, unknowingly engineering the very air that future generations of life will breathe. Earth is crafting itself into a haven, slowly, deliberately, beautifully. The stage is set. The planet has taken its first breath, and soon, life will bloom. The oceans of early Earth stretch like vast, shimmering worlds beneath the pale glow of a young sun, their surfaces shifting gently yet hiding beneath them a darkness so deep, so ancient, that even today we have explored only a fraction of their depths. Beneath those rolling waves lies a universe far older than any forest, more mysterious than any desert, and more powerful than any mountain. This is the womb of life, the place where everything that breathes, moves, grows, and dreams finds its oldest ancestor. It is a world without land, without sky, without sound, yet filled with restless creation. Imagine it, an ocean millions of kilometers wide, rich with minerals dissolved from volcanic rock, warm in some places from hydrothermal vents, icy in others beneath thick clouds, constantly stirred by tides and storms. The atmosphere above it is still far from blue. The sky is tinted with the ghostly colors of methane, carbon dioxide, and volcanic ash. Lightning forks through the heavens, illuminating the sea in flashes of electric fire. Each lightning strike, each thunderous boom, each ripple of heat contributes to the chemical dance that fuels life's earliest experiments. Somewhere in this vast, primordial sea, countless molecules collide, break apart, reform, and mutate. Most combinations fade into nothingness, but a few survive. Those few become the first cells, simple but miraculous structures capable of protecting themselves from the chaos around them. They cling to minerals on the ocean floor, drifting near the hydrothermal vents known as black smokers, where the water is heated to unimaginable temperatures by molten rock beneath the seabed. Here, in total darkness, surrounded by columns of rich chemicals, life finds its first safe harbor. These early cells multiply slowly, endlessly, and imperfectly. Each mistake in replication becomes a new possibility, a new trait, a new adaptation, a new chance at survival. Billions of years pass. The oceans remain the sole stage of existence. No creature has yet touched land. No organism has yet breathed open air. Earth is still mostly silent, except for the rhythm of waves and the eruptions of distant volcanoes. But beneath the surface, life is taking bold steps. Single-celled organisms gradually evolve into more complex structures, cells with internal compartments, with tiny engines that produce energy, with membranes that allow the exchange of nutrients. And then, after an eternity of microscopic struggle, the first multicellular organisms appear. They are small, fragile, and barely visible, yet they are revolutionary. From this point forward, life will no longer be limited to tiny, solitary forms. It will begin to cooperate, to coordinate, to build bodies with specialized parts. This is the beginning of biological innovation on a scale the world has never seen. The oceans become busier, richer, more alive. Strange, soft-bodied creatures drift like ghosts through the water. Their forms are simple yet elegant: discs, fronds, ribbons, and blobs floating gently in the currents. They have no eyes, no shells, no bones. Yet they sense their world through chemical gradients, currents, and vibrations. Millions of years pass, and slowly, evolution sharpens its tools. New life forms develop stronger bodies, harder exteriors, sharper senses. The Cambrian explosion arrives like a sudden cosmic fireworks show beneath the waves. In a relatively short stretch of geological time, Earth's oceans fill with an unimaginable diversity of creatures: spiny predators, armored scavengers, delicate filter feeders, wriggling worms, ancient trilobites with crystal lenses for eyes. For the first time, Earth is alive with movement. Predation begins. Speed becomes vital. Agility becomes a matter of life or death. Intelligence, even in primitive forms, starts to emerge as creatures navigate a world filled with both beauty and danger. The oceans become a battleground of evolution, fierce, dynamic, and breathtaking. But profound changes are occurring above the water too. The earliest photosynthetic organisms, cyanobacteria, have already transformed the atmosphere once, producing oxygen that slowly accumulates over millions of years. At first, this oxygen is toxic to many organisms, leading to mass extinction. But for those that survive, oxygen becomes a source of incredible power. It fuels metabolism in ways no previous molecule could. It enables complex bodies, fast movement, and eventually the possibility of life on land. The seas churn with innovation as fish-like creatures develop simple fins, skeletal structures, and eventually primitive backbones. Eyes become more advanced, able to detect shapes and colors. Marine plants anchor themselves to the ocean floor, forming the first underwater forests. And then, in a moment that changes the destiny of Earth forever, some of these creatures venture toward the shoreline. They crawl, wriggle, and drag themselves across muddy flats. Their fins become stronger, more limb-like. Their lungs become capable of tasting air. Their bodies adapt to gravity and to sunlight. Step by step, inch by inch, life expands its domain beyond the boundaries of the sea. The oceans, once the sole kingdom of life, now become the birthplace of explorers who will reshape the world above. Yet the oceans never lose their importance. Even today, they remain the engine of Earth's climate, the home of most of the planet's biodiversity, and the cradle of our own evolutionary story. Every human being carries the memory of the sea in their very blood, a salty reminder that our origins are inseparably tied to those ancient waters. The waves that crash onto our beaches today echo across 4 billion years of history. They whisper to us of beginnings, of struggles, of transformations. They remind us that life's greatest miracles often start in silence, in darkness, in the unseen depths of a world waiting for its chance to bloom. And in those depths, a new chapter is already forming, a chapter that will bring life onto land, reshape the very face of Earth, and eventually give rise to creatures who can look back and tell this very story. The earth beneath our feet feels permanent, solid, unchanging. Mountains stand like ancient guardians, valleys stretch quietly between them, and plains roll out endlessly, as if they have always been there and always will be. Yet nothing on Earth's surface is truly still. The planet is alive, restlessly alive, shifting, cracking, colliding, and transforming. The continents we know today are only fleeting arrangements in a much grander dance, a choreography millions of years in the making. And every step of that dance has shaped the evolution of life. To understand why Earth looks the way it does, we must start millions of years before any human eye could marvel at a mountain or trace the coastline of a continent. Beneath the crust, immense forces have been at work since the planet's fiery birth. The mantle, a vast layer of molten and semi-solid rock, churns and rolls like a slow cosmic tide. Heat rises from the core like the breath of a slumbering titan, creating convection currents that lift, drag, and tear at the plates that form the surface of the Earth. These tectonic plates are enormous slabs of rock, each one floating on the viscous mantle below. They move with the patience of geological time, mere centimeters per year, but their effects are tremendous. Where plates collide, mountains rise. Where they pull apart, oceans are born. And where they slide past one another, earthquakes ripple through the crust, a reminder that the world is still being shaped. In the early history of Earth, the continents were scattered fragments, drifting across a global ocean like isolated rafts. Slowly, inexorably, they came together. They collided to form supercontinents, enormous landmasses that merged multiple regions into a single titan. Again and again, over hundreds of millions of years, these supercontinents formed, broke apart, reformed, and shattered once more. The most famous of them is Pangaea, a colossal supercontinent that existed around 300 million years ago. Imagine standing in the center of that vast land. No ocean horizon, no distant coastline, only endless stretches of interior land, where the climate was harsh and the environment unforgiving. Rain struggled to reach the central deserts. Storms battered the coastal edges. Yet even in this difficult place, life found a way. Reptiles, amphibians, and early ancestors of mammals roamed its forests and plains. But Pangaea was not eternal. Deep beneath it, convection currents pulled at its foundations. Cracks appeared, rifts widened, lava poured from the earth like molten blood. The supercontinent began to break apart, slowly but inevitably. The fractures deepened into valleys, valleys filled with seawater, and those waters grew into new oceans. Over millions of years, the world was redivided into separate continents. Today's continents, Africa, Asia, North and South America, Europe, Australia, Antarctica, are the grandchildren of that ancient breakup. They drift across the planet even now. A few centimeters a year may seem insignificant, but given enough time, continents migrate thousands of kilometers, reshaping the map of the world over and over again. And with each shift, life must adapt. The birth of the Atlantic Ocean, for example, changed global climate patterns and ocean currents. Species that once lived together found themselves separated by growing distances of water. Evolution took these separated populations and sculpted them in different directions, creating new species, new adaptations, new ecosystems. This continental drift is one of the great engines of biodiversity, a slow but unstoppable force that ensures the story of life never stops evolving. Even today, the world's most magnificent landscapes are born directly from these tectonic forces. The Himalayas, the youngest and tallest mountain range on Earth, rise from the collision of India with Asia. This collision is ongoing, pushing the mountains higher each year. The Andes, stretching along the western edge of South America, grow from the grinding conflict between continental and oceanic plates. Deep beneath these mountains, magma rises, feeding some of the most powerful volcanoes on the planet. And then there are the ocean trenches, the deepest places on Earth, where one plate slides beneath another and sinks into the mantle. In the Mariana Trench, the pressure is so extreme that even steel would collapse like paper. Yet life survives there too, clinging to the edges of darkness, feeding on chemical energy where sunlight never reaches. The continents also shape the climate of Earth, acting as walls, gates, and platforms for atmospheric and oceanic currents. The placement of mountains can redirect wind patterns, creating rain-shadow deserts on one side and lush forests on the other. The shape of coastlines affects the flow of warm and cold ocean waters, influencing global temperatures. Even Earth's axial tilt, which gives rise to the seasons, interacts differently with land masses and oceans, creating the stunning diversity of climates across the world. As continents drift, they also carry life with them. Some species flourish in new conditions, while others vanish, unable to adapt to change. Entire evolutionary lineages migrate across millions of years, carried silently on the backs of moving plates. Imagine ancient forests drifting northward into colder climates or tropical species being carried toward regions where ice once dominated. Life, in all its forms, must either adapt or disappear. This constant geological motion also ensures that Earth's story is never static. At this very moment, Africa is slowly colliding with Europe. Australia is drifting northward toward Asia. The Pacific Ocean is shrinking while the Atlantic continues to widen. Future supercontinents will form. New mountain ranges will rise. New oceans will be born. The Earth will continue to reshape itself, carving new chapters into its surface like an artist working endlessly on a masterpiece. And when we stand upon any mountainside, or feel the tremble of an earthquake beneath our feet, or watch volcanoes spill rivers of molten rock into the night, we witness the planet in motion, a reminder that the Earth is alive, vibrant, and evolving. It is a world shaped by fire, sculpted by pressure, and transformed by time. A world whose continents drift like memories across the ocean of the mantle. A world that has never stood still. The land we call home is part of a cosmic story millions of years in the making. A story written not in ink, but in stone, magma, and the slow, deliberate movements of continents that carve the fate of life itself. There are places on Earth where time itself seems to slow, where the air is thick with the scent of rain-soaked soil, and where sunlight filters down in golden beams through a roof of interwoven leaves. These are the forests, vast, breathing worlds that blanket our planet in shades of green, stretching across continents, shaping climates, sheltering life, and whispering stories older than civilization. To walk into a forest is to step into the lungs of the earth. To listen to its silence is to hear the heartbeat of the planet. But the great forests of our world did not appear suddenly. Their origins are rooted in a deep and ancient past, a slow evolution that transformed barren landscapes into vibrant ecosystems teeming with life. To understand a forest, one must journey back to a time long before trees existed, a time when plants themselves had only just begun their struggle to colonize the land. Hundreds of millions of years ago, Earth's continents were rugged, lifeless terrains. The land surface was harsh, dry, and constantly bombarded by ultraviolet radiation. Life was still mostly confined to the seas, where it had thrived for billions of years. Yet some bold pioneers, simple algae and fungi, formed fragile partnerships that allowed them to survive on land. These early plant-like organisms clung to rocks, forming thin layers of green that softened the soil and transformed barren stone into fertile ground. From these humble beginnings came the first true plants, small, moss-like species that sprawled across damp areas. Over time, as evolution continued its relentless experimentation, these plants developed vascular systems, internal tubes that allowed water and nutrients to travel through their bodies. This innovation unlocked the possibility of height, strength, and resilience. With each new generation, plants grew taller, spread wider, and ventured farther inland. And then, around 385 million years ago, something extraordinary emerged: the first trees. They were not like the towering giants we see today. Some resembled tall ferns or strange club-shaped organisms with no leaves as we know them. Others, like the early Archaeopteryx, began to develop woody trunks and branching limbs. These ancient trees transformed Earth forever. Their roots carved deep into the soil, stabilizing landscapes. Their fallen leaves enriched the earth with organic matter. Their towering forms cast shadows that cooled the ground below, creating microclimates where new species of plants and animals could thrive. Forests spread rapidly across the continents, forming the first large-scale ecosystems on land. They altered the atmosphere as well. Through photosynthesis, trees drew carbon dioxide from the air and released oxygen. Over millions of years, this monumental exchange helped shape Earth's atmosphere into the oxygen-rich environment we depend on today. The air we breathe owes its existence to forests that lived hundreds of millions of years before the appearance of humans. As forests grew, they became cradles for life. Insects evolved rapidly, developing wings to navigate between branches. Amphibians left the water and ventured onto land, taking shelter among roots and fallen logs. Reptiles followed, then early mammals, each finding its place within the sheltering arms of trees. Forests echoed with the sounds of evolution, rustling leaves, chirping insects, and the soft footsteps of creatures whose descendants would shape future worlds. Fast forward through millions of years, through extinctions and regenerations, and Earth's forests become more diverse than ever. Tropical rainforests near the equator burst with vibrant colors and astonishing biodiversity. Temperate forests, with their turning seasons, offer cooler ecosystems filled with towering pines, sturdy oaks, and graceful maples. Boreal forests stretch across the northern hemisphere like a vast emerald belt, home to resilient species that thrive in cold, unforgiving winters. And in between all these lie unique woodland systems, each with its own rhythms and secrets. Yet forests are far more than just habitats. They are Earth's climate regulators. The Amazon rainforest alone produces vast amounts of oxygen, stabilizes weather patterns, and stores massive amounts of carbon. The Congo rainforest influences rainfall across Africa. The boreal forests of Russia and Canada act as enormous carbon sinks, helping cool the planet. Every forest, no matter how large or small, plays a role in maintaining Earth's environmental balance. The trees themselves are also natural engineers. Their roots hold soil in place, preventing erosion. Their canopies intercept rainfall, slowing its descent and reducing floods. Their fallen leaves decompose, enriching the soil with nutrients that make plant life possible. And yet, for all their ancient power, forests are delicate. A forest takes centuries to fully grow, but can be destroyed in a single season. Throughout human history, forests have been cleared for agriculture, industry, and expansion. Once they vanish, entire ecosystems collapse, species disappear, local climates shift, rivers dry, and the planet loses another piece of its oxygen-producing machinery. Still, forests endure with quiet resilience. A burned forest slowly regrows as seeds buried in the soil awaken. A logged woodland sprouts new saplings. Life returns, though often altered. A forest remembers its past, but adapts to its future. As we walk through a forest today, whether it's the dense jungles of Southeast Asia or the gentle woodlands of Europe, we are walking through millions of years of evolution. Every leaf carries the memory of sunlight captured long ago. Every branch is a record of seasons that have come and gone. Every tree trunk is a living archive of Earth's ancient journey. Look up in a forest and you see the architecture of life. Branches reaching for sunlight, leaves capturing energy, bark protecting the delicate tissues inside. Look down and you see roots intertwined with soil, fungi forming vast underground networks, insects breaking down fallen wood into nutrients. Look around and you see the forest not as a collection of trees, but as a living, breathing organism, one complex system woven together with threads of life. Forests are Earth's great cathedrals, rising from the ground toward the heavens. Their pillars are trunks, their ceilings are canopies, their stained glass windows are leaves lit by sunlight, and their choir is the endless symphony of creatures that call them home. As long as forests stand, life on Earth will never be silent. Before the first forest took root, before mountains rose from the planet's crust, and long before any creature walked upon the land, there was water. Endless water. Oceans so vast they wrapped around the entire globe, shimmering beneath a sky of volcanic haze. They were the cradle of life, the first sanctuary in which the earliest organisms emerged, evolved, and multiplied. To understand Earth is to understand its oceans, for they are not merely bodies of water, but the living heart of our world. Today, the oceans cover more than 70% of Earth's surface, stretching across the planet like immense, fluid highways connecting continents. Yet their true significance lies not in their size, but in the role they play in sustaining life. The oceans regulate global temperatures, generate weather patterns, store carbon, and produce over half of the oxygen we breathe. Every breath you take carries the signature of plankton, tiny, drifting organisms that float at the mercy of ocean currents and quietly power the planet. But to appreciate the oceans fully, we must dive back billions of years, to a time when Earth was still young and unstable. As the planet cooled from its molten origins, water vapor in the atmosphere condensed into relentless rains that fell for centuries. These rains filled the low basins of Earth with water, forming the first oceans. Into these ancient waters, minerals from volcanic eruptions dissolved, creating a chemical soup rich enough to spark the earliest forms of life. Simple, single-celled organisms, the ancestors of all living creatures, began their journey in these dark, nutrient-dense seas. Over countless generations, life grew more complex. Microbes evolved the ability to photosynthesize, capturing sunlight and releasing oxygen. At first, that oxygen reacted with minerals in the ocean, but slowly it accumulated in the atmosphere. The Great Oxidation Event, a dramatic shift in Earth's history, was driven by life in the oceans. It forever changed the planet's chemistry and opened the door for more advanced organisms. From simple beginnings came extraordinary diversity. Creatures developed new ways to swim, feed, and survive. Trilobites, ancient armored explorers, crawled across the ocean floor. Strange creatures like anomalocaridids roamed the Cambrian seas with appendages designed for hunting. Giant sea scorpions dominated shallow waters. Later, fish evolved jaws, fins became more agile, and predators grew more formidable. The oceans became arenas of evolution, where survival meant innovation. And then, around 375 million years ago, some fish began pushing themselves toward muddy shorelines. Their fins strengthened into limbs. Their lungs developed enough to breathe air. These early explorers, the ancestors of all land-dwelling vertebrates, rose from the oceans and changed the fate of life on Earth. Yet even as life flourished on land, the oceans continued to pulse with vitality. They remained home to an ever-growing diversity of species, each adapted to the unique conditions of its watery realm. Today, the oceans are divided into distinct zones, each with its own ecosystems. Near the surface lies the sunlight zone, a world of shimmering light where most marine life thrives. Coral reefs bloom with color here, teeming with fish, crustaceans, sponges, and countless other species. Dolphins leap through the waves, whales call across vast distances, and seabirds dive gracefully in search of prey. This is the ocean most of us know, alive, dynamic, and breathtaking. But beneath the sunlit surface lies a world of mystery and darkness. The twilight zone, a region of dim light, is home to strange creatures with glowing bodies, large eyes, and adaptations for the near dark. Deeper still is the midnight zone, a realm of complete darkness where pressure is immense and the temperature drops near freezing. Here, creatures evolve bizarre forms, bioluminescent fish, transparent predators, and jelly-like organisms that drift slowly through the abyss. And at the very bottom lies the Hadal Zone, where trenches cut into Earth's crust like deep wounds. In these extremely hostile environments, life still persists, feeding on drifting organic matter or surviving near hydrothermal vents where chemical energy replaces sunlight as the engine of life. These hydrothermal vents, discovered only in 1977, changed everything we thought we knew about the origins of life. Superheated water rich with minerals gushes from the ocean floor, creating ecosystems that rely not on sunlight, but on chemosynthesis, organisms converting chemical energy into life. Giant tube worms, white crabs, and strange microbes thrive here, living in environments once believed impossible. Some scientists even theorize that such underwater vents could have been the birthplace of life itself. Beyond biology, the oceans also govern Earth's climate. They absorb vast amounts of heat from the sun, distributing it across the planet through currents that function like conveyor belts. The Gulf Stream warms Europe. The Pacific currents shape weather in Asia and the Americas. Monsoons, hurricanes, and storms all draw their strength from the oceans. Without these vast reservoirs of water, the planet would be unrecognizably hostile, scorching in some regions, frozen in others. The oceans also store carbon, helping regulate the atmosphere. Phytoplankton, the tiny plants of the sea, perform a task just as vital as the forests on land. They absorb carbon dioxide, anchor it in food webs, and move it through the ocean's depths. The oceans are Earth's largest carbon sink, a natural buffer that stabilizes the climate. But just as they sustain life, the oceans also shape the fate of the continents. Waves erode coastlines. Currents transport sediments. Underwater volcanoes create new land. Earthquakes beneath the ocean floor can trigger tsunamis that reshape entire regions. The oceans are not passive. They are forces of creation and destruction. And throughout human history, the oceans have been our highways, our providers, and our mysteries. Civilizations grew along their shores, sailed across their horizons, and depended on their bounty. Even today, over 3 billion people rely on the oceans for food. Countless species depend on healthy marine ecosystems. And Earth itself relies on the oceans to maintain balance. Yet, like forests, the oceans face threats. Pollution, overfishing, rising temperatures, and acidification are altering marine environments faster than nature can adapt. Coral reefs bleach and crumble. Fish populations decline. Ancient currents weaken. But the oceans, resilient and ancient, still hold hope. Protecting them is not just an environmental goal. It is essential for the survival of life on Earth. To stand on a coastline and watch the waves is to feel the heartbeat of the planet. Every tide is a whisper of the moon's pull. Every swell is a memory of Earth's ancient past. Every horizon is a reminder of the vast, living world beneath the surface. The oceans are Earth's liquid heart, beating, breathing, and sustaining life on a scale beyond imagination. The story of Earth is not a static painting, framed and frozen for eternity. It is a living canvas, breathing, shifting, cracking, folding, erupting, healing, and endlessly reinventing itself. Every continent, every valley, every mountain range you see today is only a temporary chapter in an ancient book that has been rewritten again and again over billions of years. And though our lives pass by like a spark in the wind, the planet has all the time in the universe to sculpt its masterpiece. When we look at a world map, we imagine the continents as fixed pieces of land, immovable and permanent. But nothing could be further from the truth. The Earth's crust, the ground beneath our feet, is not a single solid shell. It is a mosaic of vast slabs called tectonic plates, floating slowly on a sea of molten rock deep below. These plates drift across the globe at the pace at which fingernails grow, yet over millions of years, that gentle movement reshapes the entire planet. Continents collide and crumple upward into mountain ranges. Oceans widen when plates separate. Land tears apart, weakening into new seas. And from the dynamic engine beneath us, the Earth's surface is sculpted in a continuous dance of destruction and creation. To understand this, imagine a world that came long before us, Earth during the age of the supercontinents. The continents we know today, Asia, Africa, Europe, the Americas, Australia, Antarctica, were once fused together into a single mega landmass called Pangaea, a colossal stretch of land that held nearly every ecosystem of its time. Before that, other supercontinents existed: Rodinia, Columbia, Nuna. Each one formed, existed for a few 100 million years, then broke apart. Earth has rehearsed this performance many times like a cosmic heartbeat. But the breaking of Pangaea set the stage for the world we inhabit now. As it began to split around 200 million years ago, molten rock surged upward, tearing deep rifts through the crust. These wounds widened into oceans, separating life, isolating species, and forcing evolution down distinct paths. The Atlantic Ocean was born from this fracture, an infant sea that expanded slowly into the giant we recognize today. And so began the slow migration of continents. Africa drifted. India broke free and charged toward Asia with impossible force, crashing into the Eurasian plate with such intensity that the Earth buckled. That collision created the Himalayas, the tallest mountains on the planet. Even now, the Himalayas continue to rise, centimeter by centimeter, as the Indian plate presses forward. Imagine mountains still growing, mountains younger than many species of trees, mountains still being sculpted by the same continental collision that began when the first mammals were evolving. But Earth's geological story is not written only in the towering peaks. It is written in the scars that run across our world, the deep trenches like the Mariana Trench, where one plate slides beneath another, the fiery arcs of volcanoes that form where continents meet, the rift valleys such as the one in East Africa, where the Earth is slowly tearing itself apart. And along the borders of plates, where tension builds, where rock resists, bends, then snaps like a giant spring, there are earthquakes, sudden and violent reminders that this planet is alive. The forces that move continents are fueled by heat from Earth's core, heat left over from the planet's formation, heat from radioactive decay, heat that constantly churns the mantle like a slow, boiling sea. Convection currents push and pull the plates like rafts on molten waves. This movement shapes climates, patterns of life, even the course of evolution. It determines where oceans rise, where volcanoes erupt, where fertile soils form, and where species flourish or vanish. Consider the Andes of South America, formed as the Nazca Plate sinks beneath the South American plate, generating powerful volcanoes and towering peaks. Their formation altered wind patterns, created vast rainforests on one side and deserts on the other. The Sahara Desert itself owes its existence partly to the movement of continents and the shifting angle of Earth's axis. Even the great ice ages were influenced by the position of continents relative to the poles. This slow, geological ballet has authored every corner of the world we love. The Grand Canyon carved through layers of rock that formed in ancient seas. The jungles of Indonesia exist because islands were thrust upward where plates collide. The deserts of Australia are the legacy of a continent that drifted away from moisture-rich latitudes. The ring of fire circling the Pacific is a necklace of volcanoes formed by multiple converging plates. And yet, for all its power, Earth is delicate. A system where each movement influences the next, where continents drifting a few centimeters can rewrite millions of years of future landscapes. Imagine the Earth millions of years from now. Africa merging with Europe, the Mediterranean disappearing, the Atlantic widening further, or perhaps beginning to close again. Maybe a new supercontinent will form. Scientists call it Amasia or Pangaea Proxima. The map of Earth is not finished. It may never be. It is always becoming. In this ever-changing world, humanity is but a brief presence. We build our cities as though the ground beneath us were eternal, but the planet has its own agenda. Mountains rise and fall. Seas advance and retreat. Islands are born from volcanic fire and vanish beneath the waves. Earth has shaped itself long before life existed, and it will continue long after. And yet there is beauty in this impermanence. Beauty in understanding that our world is not a static rock, but a living story in constant motion. A story written in stone, water, fire, and time. A story that continues beneath us, whether we see it or not. This is Earth, restless, evolving, endlessly reshaping itself through the slow breath of geological time. Water is the great architect of Earth, the silent sculptor that has shaped continents, carved valleys, filled oceans, and nurtured every living thing that ever breathed on this planet. If Earth is a story, then water is both the ink and the narrator. It is the one force that touches everything, binding past and present, geology and life, storms and seasons, continents and creatures. And long before there were forests, long before the crust cooled enough to welcome life, water was already here, waiting to write the first chapter. To understand Earth, you must understand water. Our planet is unique in the solar system not because it has water, but because it has water in abundance. Water that flows, freezes, evaporates, condenses, cycles endlessly through oceans, clouds, rivers, and living cells. Water is the reason our world glows blue from space. It is the reason life emerged, the reason climate exists, the reason continents move faster or slower, the reason Earth has remained habitable for billions of years when other planets have frozen or burned. But water is more than a necessity for survival. It is a force that shapes worlds. To see this, you must picture Earth not as it is today, but as it was 4.4 billion years ago, young, molten, battered by meteorites and storms of cosmic debris. The atmosphere was thick with steam and volcanic gases. Rain fell not in gentle drops, but in endless, planet-wide storms that lasted millions of years. Oceans formed slowly, pooling into the newborn basins of our cooling crust. Imagine the entire surface of Earth shimmering with boiling seas, the first oceans emerging under a sun still half as bright as today. Where did all this water come from? The truth is still a mystery. Some scientists believe it formed from volcanic outgassing, hydrogen and oxygen released from Earth's interior. Others think icy comets and water-rich asteroids delivered it during violent impacts. Perhaps both are true. But however it arrived, water did something extraordinary. It changed everything. It cooled our planet, stabilized the climate, dissolved minerals, and became the cradle of life. Oceans turned Earth from a barren sphere of rock into a blue world overflowing with possibilities. Today, those oceans cover more than 70% of the planet, vast, deep, and largely unexplored. In fact, humanity has charted more of the moon's surface than the deepest trenches of its own oceans. Beneath the waves lies a realm of darkness and pressure so immense it could crush steel. Yet life thrives there in forms so unique, so alien, that they remind us how little we truly know. The hydrosphere, Earth's global water system, is divided among oceans, rivers, lakes, ice sheets, groundwater, and vapor in the atmosphere. But oceans hold almost all of it, 97%. Those oceans control the climate with a precision so delicate that even small changes ripple across the globe. They absorb heat from the sun during the day and release it at night. They carry warm water from the equator toward the poles and cold water from the poles toward the equator, balancing temperatures and creating weather patterns. Every storm you've ever witnessed began as a conversation between ocean and sky. Every cloud, every raindrop, every breath of wind. The oceans evaporate constantly, sending water into the atmosphere, where it condenses into clouds and falls again as rain or snow. This water cycle sustains forests, feeds rivers, fills aquifers, and supports agriculture. Without it, Earth would be a desert world. And yet, water is not only gentle, it is powerful, even destructive. Over millions of years, rivers carve canyons deeper than skyscrapers. Glaciers grind mountains to dust, carrying rocks across continents like silent bulldozers. Waves sculpt coastlines, pushing land back inch by inch. Floods reshape valleys. Storms redraw shorelines. Water weathers stone, dissolves minerals, and transforms landscapes so slowly that our human eyes barely notice. Consider the Grand Canyon, a masterpiece carved by the Colorado River over 6 million years. Every layer of rock exposed in its walls is a page of Earth's history written in sediment and time. Or look to Scandinavia, where ancient glaciers once towered miles high, scraping away mountains and leaving behind lakes and fjords that now define entire countries. But water shapes not just geology, it shapes life itself. It dictates where plants grow, where civilizations form, where animals migrate. Ancient human settlements thrived along rivers like the Nile, Tigris, Indus, and Yellow River because water meant survival, agriculture, transport, and power. Even today, half of humanity lives within a short distance of a coast. Our world economy depends on oceans: shipping, trade, fishing, energy, climate control. And deep beneath the oceans, something miraculous happens. Life persists in absolute darkness. At hydrothermal vents, cracks on the seafloor where superheated water erupts like underwater geysers, organisms thrive without sunlight. Bacteria use chemicals instead of sunlight to produce energy, forming the base of ecosystems so alien that they resemble deep space worlds more than Earth's surface. These vents may resemble the environment where life began billions of years ago. Water also holds Earth's memory in ice. The polar ice sheets of Antarctica and Greenland are frozen archives of climate history. Trapped inside their layers are tiny bubbles, ancient air from thousands or even hundreds of thousands of years ago. By studying them, scientists can read past climates like diary entries etched in ice, revealing times when Earth was warmer or colder, wetter or drier. But the oceans today are changing. Warming waters threaten coral reefs, rainforests of the sea. Melting ice raises sea levels, threatening coastal cities. Shifting temperatures disrupt currents and weather systems. Just as water has the power to build, it also has the power to warn us. It tells us when the planet is out of balance. It responds faster than rock or soil. It signals change with storms, droughts, and rising tides. And yet, even with all our technology and knowledge, we have explored only a small fraction of the oceans. In the darkness below 200 meters, sunlight fades. Below 1,000 meters, the world is pitch black. Below 6,000 meters, only the deepest trenches remain, silent, crushing, mysterious. Down there, new species await discovery, strange and beautiful in ways we have not yet imagined. Water is the blood of Earth. It flows through rivers like veins, circulates through oceans like a heartbeat, rises into the sky like breath. It connects every living thing. It created us, sustains us, and will shape the future of our world long after we are gone. And that's where we'll pause for today. I hope you enjoyed this little long journey into the Milky Way. We'll continue the next part tomorrow, so make sure to come back, get comfortable, and drift into more sleepy science facts with us. Until then, rest well, stay curious, and I'll see you in the next episode.